Okay, thank you. Hello, everyone. I'm Wenjie from Tsinghua University, and today I'm very honored to be here to introduce our work about retrieval-enhanced vertical fed recommendation for full-set user benefit. And this is the joint work with colleagues in Tsinghua University and Meituan. And today my presentation is divided into 5 parts. The first part is about background and motivation, about multi-platform recommendation, and then our key ideas about using retrieval augmentation to solve problems in this area, and then the methodology, the experiments, and conclusions. At first, let me show some cases about our business scenarios. If you open the mobile app of Meituan and scroll down the screen, you can see several information cards showing the screen, and among 10 information flow cards, there may be one advertising card inserted, and that's what we call information flow advertising. And it's one of the key business in Meituan. Here, I want to emphasize that the information cards is cross-domain, and the recommendation result, the multi-domain recommendation result is back-ended and managed by different departments and teams. The data and the business are sometimes isolated. And that is to say, when we extend this scope to multi-platform, it becomes severe. That is, usually user intention data is scattered in multiple mobile apps or platforms in his cell phone. And although directly collect them to train a joint recommendation model may produce more accurate prediction results. However, we cannot do that because of privacy regulations and because of some business confidential regulations. So here the core question is that, can we conduct multi-platform recommendation in a privacy-preserved way? And in reality, we must do it in this privacy-preserved way. And a common answer is vertical federated learning. That is, 2 or more parties can collaboratively train a distributed model with the model and data both privately owned and never been revealed. For example, in this figure, there are active party A who holding the label and some features about the user, and the passive party B holding another kind of features about same users. The 2 parties can independently extract representations from their bottom model, and in the forward pass, the passive parties can send the representation to the active party. The active party aggregates all parties' representation and finish the succeed forward pass. So in this whole process, only the intermediate results are transferred, and thus the original data is protected. And this basic fashion of vertical federated learning has been widely applied in industry. For example, in China, the ByteDance, Tencent, and Jingpeng has also applied this technique in federated advertising and acquire significant business success. However, the basic solution of vertical federated recommendation has 2 main drawbacks. The first one is about the reduced training sample space, because the federated model must train on the aligned data, and this will restrict the user group interest awareness of the model. And second, the federated model needs all parties' features to make prediction. Thus, only the aligned users can benefit from online serving of federated models. However, aligned users usually constitute a small portion of all user sets of a company. Thus, we need to, besides building a distributed federated training system and a real-time federated inference system is expensive. So this challenge hinders the real application of vertical federated learning. And in the worst case, even aligned users cannot benefit from federation. Once, if the importance of additional features embraced by federated learning is less than the importance of the reduced user samples in local part. We can see that in this figure, the performance of federated model is far less lower than the performance of original local model with all users. That is to say, the advantage of feature extension must cover the loss of user reduction for vertical federated recommendation to be effective. So we ask, can we build a vertical federated recommendation system with full set user benefit? And that's the main topic of this paper. And first, to achieve this goal, we redefine the problem from traditional ReFer to fully ReFer. And the first goal is to utilize all user data during training. And the second goal is to achieve full-set user inference and benefit. That is, the model trained on the fully ReFer must outperform both local model and traditional vertical federated learning model. This goal is not trivial to achieve, and it has two main challenges. The first challenge is the intrinsic data missing problem of the unaligned user. And the second is the user group bias inherently existed between the aligned and unaligned users. So how can we truly achieve the goal of fully ReFer? And we propose a retrieval augmented framework named ReFer to tackle this challenge. ReFer is a two-stage framework. The first stage is augment each sample with our retrieval mechanism. And second, fuse the retrieval results with a query to enhance representation learning. And ReFer consists of two retrieval mechanisms. The first is the cross-RA module that conducts cross-domain retrieval to tackle the data missing problem. And the second component is local RA. It conducts mutual retrieval for both user sets to alleviate the problem of group bias. And the basic idea of that, but the core challenge is that in a distributed and privacy-preserved setting, it's not trivial to achieve an effective and efficient retrieval mechanism. And that's our main contribution. And here is the overview of our ReFer framework. And in one sentence, the goal of ReFer is to that given one user item pair from the active party in the left, ReFer will return k retrieval results for both parties and then fuse them in a reasonable way to enhance the model, to enhance the representation learning. And thus ReFer consists of two parts. The first part it is a hierarchical federated retrieval component, consists of a user retrieval and a sample retrieval. And the second part is about a federated fusion module that fuse all the retrieval results in local side and cross side. And let's first show how the two retrieval goals was achieved. That is, for local RA, the goal is to retrieve a side feature for all user queries. And here the candidate pool is a 4-user set. It is a relaxed version of mutual retrieval. That is, for each user in unaligned user set, it has potential to retrieve similar users from both the unaligned set and aligned set. But for the cross-RA module, its goal is to retrieve B-side feature for all users. And here the candidate pool reduced as the aligned user set because in the federated setting, only the aligned users have both side features. And for unaligned users, although it did not have ground truth features in B side, we can select k relevant users features from the aligned user set as a proxy to represent its characters. And that's how it solved the problem of data missing. And the two above retrieval mechanisms share the same user retrieval and sample retrieval. The zero retrieval can be implemented by any parameterized model which can produce user embedding for each user ID. And our framework did not restrict the choice of user retrieval. In our experiment, we found that the retrieval training data source can vary from different domains. And besides, the model can be as simple as matrix factorization to produce overall good performance. And we just choose the common used dot product operation as a similarity metric. For the sample retrieval, any arbitrary parametric or non-parametric ranking operation are all supported. But in our experiment, we find that although the most simple times closeness best item retrieval is enough to produce significant good performance. So let's summarize the retrieval efficiency and security about our retrieval mechanism to check whether it fulfills the demands of the vertical federated learning setting. First, the two-staged retrieval mechanism has the overall sublinearity complexity. And for the security, the overall retrieval process only need to transfer some aligned user ID and sample time to the passive parties, and this information are common knowledge between all the parties. So it did not break the privacy restriction about the wave file setting. And besides, this data only introduces minimal communication burden because they are all ID informations. Finally, the retrieval process of our framework is industry friendly. First, it supports arbitrary user embedding, and second, it supports very simple embedding models. Finally, one do not need to build a retrieval system from scratch. It can just reusing existing recall systems in the original recommendation system for our retrieval stage. So once we acquire k relevant samples for each query, the retrieval module will fuse them as one final retrieval vector. But here we have different kind of data. For example, the unaligned users and aligned users, and the data in passive party and the active party. So the total cases for data fusion have 4 cases, but the cases in local part share the same fusion structure. We can just adopt the standard cross-attention to fuse the k samples into one final compact representation. And the most special fusion part is about the fusion of vectors from unaligned users in passive parties. We must compact the vectors and send it to the active party to conduct the fusion, because there are no ground truth B-side features to for us to conduct cross-attention in B-side. So we must transfer it to the active party. And before we fuse them in the active party, we must project all the representation vectors into one domain. And then in that domain, we mirror the similarities about the retrieval results, about the query, and then conduct a weighted sum to get the final representation vector. And the process for the aligned users in cross-party is the same, but do not need the distributed communication process. So that's all the introduction about the method part. And before we introduce the experiments datasets, I need to clarify that there are 2 main task types in vertical FAIR recommendation. That is the attribute wave setting and the sequential wave setting. The goal of attribute wave setting benefits from the additional features from passive parties. And in the sequential wave setting, the goal of federated learning is to leveraging sequential features from another domain. And we have conducted experiments on 3 datasets. 2 of them are sequential wave setting, and one of them is the attribute wave setting from industry data. And the dataset has 2 parties. Each party, one of the party was the browse domain, and another party represents for the search domain. And our experiments focus care about the 3 main research questions. The first is about how much can ReFer outperform the baselines in overall user performance. And the second question is whether each user group can benefit from ReFer compared to baseline method. And the third part is about the flexibility of the retriever. And there are 3 sub-questions to validate its effectiveness. So the first, we can see ReFer achieves the best performance among all baselines when we evaluate it for the 4-set user performance. That is, for example, the AUC and the negative log likelihood for all users. And second, that's the main claim of our paper. That is, ReFer can achieve per group user benefit. That is, no matter for unaligned users and aligned users, they can both outperform local model and federated model. And third, for the flexibility of the retriever, the first part is about retrieval size. We can see that as the retrieval size increases, the performance of local IA and cross IA will achieve optimal peak and then down. So a proper retrieval size is critical to achieve the best performance. It is reasonable because too much retrieval will introduce noises. And we can also say that both of local IA and cross IA works, and the performance will be better if they are mixed. And the second key question is, because our cross retrieval module relies on the candidate set of aligned users, so we want to discuss whether the ratio of aligned users impact our effectiveness. And the result is that ReFer will also performs good in very low aligned data ratio. And finally, we want to show the flexibility of the user retriever. Here we show that no matter one use the in-distribution data or out-of-distribution data to train the user embedding, ReFer also outperformed baseline methods. And finally, let's make a conclusion. First, we established a brand new collection of retrieval-enhanced machine learning and our vertical fed recommendation problem. Second, we proposed the first retrieval-augmented vertical fed learning framework to achieve the goal of fully ReFer. And finally, we conducted comprehensive experiments on both industry data and public data to validate our method's effectiveness. And for future direction, we may explore more fine-grained design for user retrievers and sample retrievers to fulfill different kinds of demands in different settings. And second, we want to explore the potential security issues embraced by our new framework based on retrieval augmentation. And that's all my presentation. Thank you all very much.